Hey everyone, welcome back. In this video, we're going to look at a hypothesis test for a population mean. So we're going to go back and revisit in another example we've seen when we were constructing confidence intervals. We're going to go back to our manufacturer of small appliances. If you remember, we had a sample of 50 stores in the Midwest region. They were asked to give the number of electric can openers that they sold in the last month. So we were given the data. We're also given the mean, right, which is from our sample of 23.65 and the standard deviation of 12.64. But now instead of constructing a confidence interval, we're asked to use an appropriate test to determine if the average number of sales at all stores is not 19. So from our question, right, we obviously have, I'm gonna write this up here. We need to state our null and alternate hypotheses. And I've already mentioned, right, that it is a test for a mean. But you can see in the question, right, we're pretty clearly asked if the average number of sales is not 19, right? That average number gives it away. And then also in this part of the problem, we're told that they were asked to give the number of manufacturers, the number of sales, right? And we took the mean of that data, right? The average of it. So this is a test for a population mean, right? We need to put our population parameter mu. We always put the equal to sign in our null hypothesis. We want to test to see if the mean is not 19. So 19 is the value of interest that we have, right? And so because we want to see if test that the average number of sales is not 19, well, that means it could be greater than, it could be less than, right? So because it could be either or, we'll use the not equal to sign. And again, that same value of interest, right? 19 goes in our null hypothesis. Not equal to, right, is not 19. And this means, remember the nickname for this, when we have the not equal to sign, is a two-tailed test. So we're going to have to find the area under the curve above and below the positive and negative value of whatever t-score we find, right? We're going to have to use t-values here for our population mean. Step 2, we just state our level of significance, which is our alpha. And we're given in the problem to use alpha equals 0.05. In step 3, we state our statistics. When we're talking about a sample mean, we have 3 statistics, right? We have our sample size, our sample mean, and our sample standard deviation. These were all given to us on the last slide. We can fill this out. A random sample of 50 stores, right? So our sample size is 50. And then we're given the mean of the data, right? So the mean of our sample is 23.65. And the standard deviation is 12.64. Okay, so on to step 4. This is where we're going to calculate our test statistic in part A of step 4. For a hypothesis test about a population mean, we need to calculate a t statistic, right? So we take our sample mean, subtract it from our mu naught, right, which is the population mean in our null hypothesis. And then we have to divide all of that by our standard deviation divided by the square root of n, our sample size. We have all of this information, right? So we can just plug everything in. Our sample mean was 23.65. The population mean we're assuming from our null hypothesis is equal to 19. And then that standard deviation was 12.64. And that can be divided by the square root of 50. So 23.65 minus 19 is going to be 0.65, should be, yep, 4.65. And then let's just take the square root of 50 as well. The square root of 50 is 7.07. Some change, so 4.65, we'll leave that in the numerator. Now let's do 12.64 divided by 7.07. I get 1.7, call it 8. And then finally, if we divide 4.65 by 1.788, we get a t-value of 2.6. I've lost my mouse again, sorry about that. So I get a t-value of about 2.6006, so we'll just leave it at 2.60. Okay, so let's, oh, almost forgot a statistic up here that we need. Our degrees of freedom, this is equal to n minus 1. This is our sample size, right? 50 minus 1, so we have 49 degrees of freedom, right? We need to know how many degrees of freedom we have to know which specific t distribution we need to use to find the area under the curve for this t value, right? So let's go back a few slides here to our t table. I wish I could hide these drawings as opposed to just deleting them. But if you remember, the t-table is a little different than our z-table, right? The t-table has t-values on the inside of our table, and it's got the areas under the curve up here in the margins, upper and lower margins, and then we have our degrees of freedom out here to the left. Whereas our z-table had areas under the curve on the inside of our table, z-values were on the outside on the margins, right? So we have a t-value, and we want to try to find the area under the curve of this t-value for the specific t distribution, right, with 49 degrees of freedom. So the closest we can get really is 40. So if we go along 40, you can kind of see an issue here, right? We've got a t-value of 2.4 and a t-value of 2.7. And 2.6 is obviously somewhere in between there. It's a little closer to 2.7, so let's come up. You can see we do have a nice option here, right? For a one-tailed, think of this as a one-tailed test, right? Cumulative probability. So 0.005 is the area under the curve on one side of 2.704 with 40 degrees of freedom. Probably the upper, right? And then 0.01 would be our two-tailed, which we do have a two-tailed test here. So this would be the area underneath negative 2.7 and above positive 2.7. So let's just keep that in the back of our minds. Maybe I'll write it down here. And I am getting a little ahead of myself here, aren't I? Because we really need to draw out our picture first. So part A, we calculated our t-value. Let me back up just a minute. So in part B, we can draw out our t-distribution. Right, we have a t-value of 2.6. And we need to determine, right, do we want the area, do we want a one-tailed test or a two-tailed test? Do we want the area under the curve to the left of this positive 2.6? Do we want the area under the curve above it to the right? To answer that question, we need to look at the inequality in our alternate hypothesis. We have a not equal to sign, and the nickname for that not equal to sign, right? When we see that in our alternate hypothesis, the nickname is a two-tailed test. So what this tells us is we want the area under the curve to the right of positive 2.6. And we also want the area under the curve to the left of negative 2.6. We want both tails, want the area under the curve of both tails. And we use this negative 2.6, right? Because it's the mirror of the positive 2.6 we calculated. So how can we find the area under the curve? Well, we just saw, right, that 0.005, this was according to our table, right, with a true t-value of about 2.7. So if we use the table value, which isn't really ideal, right, because it was A, not the right amount of degrees of freedom, and B, it wasn't the exact t-value. If we add these two together, we would get a total p-value of 0.005 plus 0.005, right? We're adding both sides together. So the total area under the curve would be 0.01. So now let's go use our calculator and see if we can get a better answer. So I'm going to stop sharing. It's going to make us lose all of our drawings, but you can back up. Go ahead and back up in the video. So we're going to go to the familiar second vars to take us to the distribution. And we're going to go down now to option 6, which is our TCDF, we have a t-value, right? And we want to find the area under the curve to the left and the right. So it gave me a negative infinity to start with. So I'm going to plug in our negative 2.6, and I'm going to just find the area under the curve from negative infinity just up to 2.6, right? That'll give me one side, and then we can just double this, right? Because the area under the curve from 2.6 to positive infinity is the same as the area under the curve from negative infinity to negative 2.6. We can put in our exact degrees of freedom, 49, can enter all that in, and we actually get an area under the curve of 0.006. So if we go back to our slides, oh, I'm sorry, I wasn't sharing my screen at all there. Hang on, let me share my screen again. Can walk back through this. So I went to second vars for the distribution. We can go down now to option 6, which is our TCF, right? We have a t value. We're looking for the area under the curve of that t value. And remember, because we're looking at two tails here, we want the area to the left of negative 2.6. And then our upper tail, right, we want the area above the curve of positive 2.6. Those areas are going to be the same because of the symmetry property, right, of our t distribution. So I'm going to find the area under the curve from negative infinity to negative 2.6 with 49 degrees of freedom. And enter all this in, and I get a t-value actually of 0.006. And so this is you might think, well, you know, that's pretty close, 0.005 or 0.006. So here, our true p-value is equal to 0.006. Can multiply by 2, and we get 0.012. This is in step 5. This is less than alpha 0.05. But imagine we were told to use alpha 0.01, and this becomes greater than 0.01, right? So using that table, we would have only gotten 0.01, which exactly equals it. But calculating the p-value properly, right, with our calculator, plugging in the exact number of degrees of freedom and the exact t-value can impact, right, step 5 and our step 4. So it's best to use the calculator to calculate that t-value for these hypothesis tests. In step 6, with the results we got, when your p-value is less than your alpha, you reject HO. There is significant evidence to suggest or support, right, HA, the population mean, the average number of sales at all stores is not 19. Okay. This pretty much wraps it up for chapter 22 and chapter 23, which is, I'm sorry, chapter 19 and chapter 22, hypothesis tests. So next we'll start on chapter 23.